Professor Urunobu Chakraborty to introduce the speaker and take charge of the session. So, AC sir, please. You can continue.
Okay, thank you, Sovik. Thanks very much. Okay, welcome everybody to the afternoon session and a very warm welcome to my friend Professor Ricardo Diaz from Portugal. Ricardo, welcome to Presidency Physics for this meet. Before you start talking, it's just we have planned to give a very short introduction to about the speaker. So just let me tell the audience that. Professor Ricardo Diaz, he did his PhD in the Interdisciplinary Research Center in Superconductivity University of Cambridge several years ago, and then from 2000 he has been in the department of physics department of the University of Aveiro in Portugal. He is a professor there. About his research interests, throughout his career, Ricardo has focused on the study of electronic correlations and topological effects in systems with low dimensionality, geometric frustration, and singular density of states. These are very interesting objects of study, and this is one area where a huge part of the world is now focusing attention on. And presently, Professor Diaz is a member of the Associate which is the Institute for Nanostructures, Nanomodeling, and Nanofabrication. And he is presently the head of the Quantum Transport Research Group and the president of the Scientific Council of the I3N Aveiro. So with this brief introduction, I again heartily welcome our friend Professor Ricardo Diaz to deliver his talk. Ricardo, the screen and the audience both are yours now.
So, hi everyone. Thank you very much for the introduction, and thank you the organizers and also Professor Anava for inviting me to give this talk. So the title of my talk is I Root Topological Insulators, but before that, let me just repeat a little bit of what Professor Anava told you, which is I'm the coordinator of a quantum transport group at the University of Aveiro. This group is a part of a large institute with more than 100 researchers called I3N. It works in nano stuff. It has two centers, one in Aveiro, the other one in Lisbon. My group has 3 researchers and a few students, and we do have quite a few collaborations, mainly with groups in the United Kingdom, Spain, and also in Portugal. So Aveiro is a small city in the center of Portugal, and it's partially surrounded by a saltwater lagoon. So you get these very nice pictures. We have a few channels crossing the city. So yeah, it's a nice place to visit if you want to come. The University of Aveiro is fairly young. It's only 50 years old, and it's quite small. It has about 15,000 students. And it's mainly focused in engineering degrees, okay? So the outline of my talk is going to be the following. I'll spend some time introducing basic notions of topological insulators, and then I'll present a particular set of topological insulators that do not follow the usual topological characterization. And that's going to motivate the next topic, which is the square root topology in condensed matter. Then I'll try to generalize this concept of square root topology to high root topology. And I'm going to do that introducing first a particular set of one-dimensional models, which we call n-time squareable sine-cosine chains. And then I'll present a general method for construction of high root topological insulators. And then I'll summarize, okay? Okay, so if you want to look up some more details about what I'm going to show you, you can look up these references over here, okay? The ones from last year's are the most important. Okay, so what is a topological insulator? Topological insulator is a material that has an insulating bulk, but conducting edge states, okay? This is what we call a topological phase. And if you change the physical parameters of this system, it may lose this behavior in what we call a topological phase transition, and it goes into a trivial phase. This topological phase transition is different from the usual continuous thermodynamic phase transitions where you have symmetry breaking. Here there is no symmetry breaking. Also, this topological phase may occur in finite systems. We don't need the thermodynamic limit. Also in the topological phase, the edge states may be protected by symmetries, okay? And more importantly, we do not have a continuous Horner parameter like in the usual thermodynamic phases. Instead, we have some quantities that take integer values and that we call topological invariants. So how do we justify the existence of these topological invariants? I'm going to follow a particular path. which is this one that you see here, from the magnetic monopole to the two-level system to the topological insulator, okay? But before that, let me just show you a very simple example of topological invariant that these objects, okay? One such property is the number of holes. We call this number of holes genus number, the genus number. It's fairly easy to see that you can change this donut into this over here, okay? And while doing that, the number of holes is still one, okay? So the genus number is one, and these two objects belong to the same topological class. Okay, so let us go now to the magnetic monopole. I'm waiting for the slide to appear in your screen because, oh, it took, I had to go one.
Yeah, it's
okay.
fine.
So now you're seeing, it's fine, it's fine.
Yeah,
so
it's fine.
Let's assume a magnetic, right? Okay. Let's assume a magnetic monopole, okay, centered at the origin of our system of coordinates that generates this B magnetic field here on the left, okay, okay, and the strength G, okay. So if we have, I know that we don't have monopoles in real, in nature, you know, guys, but let's assume that there is such a monopole. If we know the magnetic field, we can also define the vector potential, okay? And between vector potential and magnetic field is the usual one. So the curl of the vector potential gives you the magnetic field. And when we have magnetic field and vector potential, that allows you to calculate magnetic flux in two ways, okay? You can do the surface integral of the magnetic field, like here, or you can do the circulation of the vector potential along a path that runs the surface where you are basically determining the magnetic flux, okay? So, for instance, in the case of the magnetic monopole, the magnetic flux through a sphere of radius r is going to be 4 pi g, okay? It's easy to see, even looking at the picture. But if you divide the hemisphere, if you divide the two hemispheres in two halves, then you can also calculate the flux doing the circulation of the vector potential along this loop over here, okay, this circle, plus the circulation of the vector potential along this, again, same loop for the south hemisphere. But if you look at these two pictures, you'll see that the circulations have opposite directions. So the sum of these two circulations gives zero. So the magnetic flux is zero. But that's wrong because we know that magnetic flux is not zero. So what happens? What's wrong here in this analysis? What's wrong is that we assumed that vector potential was a smooth factorial function. But it's not. In fact, it has a line of singular behavior. It starts at the monopole and extends to infinity. And whatever you choose, you will always have this Dirac string. We call this line of singularities a Dirac string, okay? So let's now jump to two-level system. The most general Hamiltonian for a two-level system, excluding global shifts of energy, is this one that you see here, where the cursor is, okay? And if you look at this matrix, you will conclude that it's a linear combination of Pauli matrices, okay? And the components of this linear combination define a 3D vector that here we call D, okay? D, it's this vector over here. D, sorry, okay. And if you find the eigenvalues of this matrix, you get plus and minus the magnitude of D. And if you find the eigenbases, these eigenbases can be written using the spherical angles of this vector D. So theta and phi are the spherical angles defined by the vector D. And this eigenbasis is defined up to a global phase, but I'll talk about that in a second, has the same problem as the vector potential in the case of the monopole. And what is the problem? Is it's not well defined in one point of the Bloch sphere. When theta is equal to pi, you see that this state over here will be zero, the bottom component, and the top component will be exponential of minus I phi. And phi is not well defined in south pole. Okay, if you multiply these eigenbases by a global phase, you can remove this problem in South Pole, but it will appear somewhere else in the Flock sphere. Okay, so it's very similar to the monopole. So maybe we can define also vector potentials and magnetic fields in the case of the two-level system. And in fact, we can, okay? And that's what you have here. I'm going to define the vector potential, let's call it the Berry vector potential, or if you want, the correct name is the Berry connection, as the terms that appear in the first order correction in the deviation of the overlap of this state with itself when I change slightly the changing the value of theta and phi. And so the vector potential is going to be defined. It will have two components, one for the derivative in relation to phi and the other one in relation to theta. The vector potential will be defined like this, okay? And now that we have a vector potential, we can define a magnetic field, okay? A Berry magnetic field. We call it Berry curvature, which is just the curl, okay? Since we only have two components for the vector potential, this magnetic field will be a pseudo-scalar, okay? So it's, but anyway, we now have vector potential, we have magnetic field. We can calculate magnetic flux. We can calculate magnetic flux through using circulation of the vector potential, and that's what we call a Berry phase, or we can calculate from the surface integral of the vector of magnetic field, in this case, Berry curvature. Our surface is now the parameter space of the theta and phi. So if we do this for the eigenbases that I have in the previous slide, we get this integral over here. And if you look closely to the form of this integral, you'll see that we can interpret it as the flux of a radial vector that has magnitude 1/2 through a sphere of radius 1, okay? And the result gives 2 pi. Okay, I'm going to divide this 2 pi by 2 pi, so it gives 1. And this is going to give you the most important topological invariant in topological band theory, which is the shared number. So the shared number is just the total Berry flux divided by 2 pi, okay? So we have a flux. No? We have an integral that we say that it's a flux. Where does this flux come from? Well, one way of understanding where it comes from is, again, to define the vector potential, but now not varying the theta and phi, but instead varying the components of the d vector. So we are going to change the components of the d vector, dx, dy, dz. And that's going to give us a vector potential that now has 3 components, okay? The definition of the vector potential, or the very vector potential, is the same, is basically the corrections in first order that we get to the overlap of the eigenbases when we change the d vector, okay? We could interpret this as a phase, but so if we now define the vector potential like that, we can calculate the Berry curvature. Again, remember that this is the magnetic field, and the magnetic field has this expression. So it's very close to the expression that we had for the magnetic monopole. But in the case of the magnetic monopole, the denominator was r squared. Here we have d squared. So the origin of our flux is the point d equal to 0. D equals to 0 is where we have our effective magnetic monopole, okay? And what means d equals 0? It means that the two levels are degenerate. So when I have a degeneracy, it creates flux, this Berry flux, okay? So how is this relevant to topological insulators? Well, let's consider the most simple example of a topological insulator. The most simple example of a topological insulator is the SSH ring, okay? And or the SSH chain, if you want. The SSH chain is a 1D system with alternating hopping terms, or alternating hopping constants. T1, T2, T1, T2, T1, T2, and so on. So it has a unit cell with 2 sides, okay? Let's assume periodic boundary conditions. So we have a ring, and let's find the eigenstates and eigenvalues of this Hamiltonian, this Twainian Hamiltonian. Well, we already know the eigenstates. They are log states, okay? Because this is a periodic lattice. They are log states. Since the unit cell has two sides, then our block states will be of this form. The tensor product of a plane wave correspond to the unit cells times tensor product with a spinor with two components, A and B, which are amplitudes in the unit cell, sides of the unit cell, okay? Fixing K, we can reduce this large matrix to a much smaller matrix, which is where this K, which is the bulk, what we call the bulk Hamiltonian, and the spinor, okay? I'll call it block state. And this Hamiltonian, in the case of the SSH model, has this form over here. It's a 2x2 matrix. So you can see already the relevance of the two-level system to this topological insulator. Okay, but let's go into that in a second. So this is the bulk Hamiltonian. If I diagonalize this Hamiltonian, I get the band structure of the SSH model. And this structure is the following. For T1 equal to 0, I get flat bands, what you see now, okay? And as I now increase T1 with T2 fixed, so I increase the ratio T1 over T2, the band gap reduces until the top band and the bottom band touches at k equal to pi, okay? And the band gap opens again, okay? So that's what we have here. To do the same the Berry connection, and I'm going to define a magnetic field, Berry curvature, okay? I'm going to do this for a more general model than this one, okay, in order to give you the general expressions, because this is a 1D system. Let's do this for a 2D system, 2D or 3D, okay? The only condition I put here is that, again, I have a unit cell with two sides. This is some sort of two-dimensional system. These are the two bands that it has. Of course, we have now momentum with two components, kx and ky. If it's three-dimensional, we have three components. But the idea is the same. We are going to define our Berry connection, so our vector potential, as the first-order corrections, or the terms that appear in first-order corrections to the overlap of the eigenstates, and here it's the spinor that I mentioned before, when I change k, okay? When I change the components of the k vector of the momentum. By doing that, I can then define the Berry curvature, which is our magnetic field, and I can define the magnetic flux and divide it by 2 pi in order to get the Chern number, okay? Again, I'm not going into detail, but if I have a degeneracy, that will create magnetic flux and then will generate a finite Chern number. What is degeneracy in this case is the top band touching the bottom band. That's what we saw just a while ago in the SSH model. For T1 equal to T2, they would touch, okay? So let's go back to the 1D system. So I have this bulk Hamiltonian for the SSH model. I'm going to call this off-diagonal matrix element, I'm going to call it rho. Rho, it's a complex number, okay? So it has some absolute value and a phase. And the eigenvectors of the SSH model can be the spinor can be written in this phase. So it gives this result. Really to go in detail here. The problem, which is now k is a scalar. It only has one component. The momentum only has one component because it's 1D system. So I don't get the vector. I cannot define a Berry curvature, but I still can of the Berry connection. What I do when the momentum goes from minus pi to pi of my vector potential, which is my Berry connection, which in this case is just a scalar. Okay, and if I replace these eigenstates here in this expression, then I will get this expression here in the bottom. If you look at this expression in the bottom, it's telling you the following. The Berry phase, which in this case, we call it Zach's phase, okay, for this system, we call it Zach's phase. The Berry phase, or the Zach's phase, is going to be 1/2 let's call it the sum of the variations of the angle phi, okay? So I'm going to change the angle phi, changing k, changing the momentum, phi is going to change, and I'm having all these variations, and the Zach's phase is 1/2 the sum of all these variations. So it's easy to see that we'll have two regimes, okay? And the two regimes are T1 larger than T2, T1 smaller than T2. And why do we have these two regimes? Because rho, look at the form of rho, is T1 plus T2 a phase, okay? And in the complex plane, that means that rho is this dashed line, dashed red line, and it's the sum of this real number with T2, which is also real, but multiplied by the phase gets an angle, okay? And now when K is changed from minus pi to pi, this vector here, let's call it a vector, it's going to draw a circle. It's going to rotate around this point and draw a circle. And we have two situations, which is if T2 is smaller than T1, this circle will not enclose the origin of the complex plane, will not enclose. But if T2 is larger, it will enclose. It's what you see here in this picture here, okay, guys? And in fact, if you add all the variations of phi, and phi it's this angle over here, if you add all these variations of phi, the total variation in this case is going to be 0, but in this case over here, it's going to be 2 pi if I add all these variations. And multiplied by 1/2 that we had in the previous expression, it gives pi, okay? This is very similar to the monopole, because I told you that the level degeneracy meant bands touching. And in fact, the origin of the complex plane is the point where rho is equal to 0. And when rho is equal to 0, and that means k equal to pi, oh, no, I'm not going into more detail, I'm just going to say the bands touch. Rho equal to 0, the bands touch. It's this point over here if you want to. This is a different plot of the bands. The bands touch. So what I'm saying here is the Zach's phase is finite if the monopole, let's call it monopole, it's inside the circle. And Zach's phase is 0 if the monopole is outside the circle. Okay. And what happens if the SSH chain has open boundary conditions? So basically, it's not a ring now. We basically take a scissor and make a cut. So it's a chain with open boundary conditions. What happens is that the SSH chain will have edge states if T1 is smaller than T2, but in what we call the topological phase, okay, where the Zach's phase is equal to pi. But in the trivial phase, when the Zach's phase is equal to 0, we don't have this. And this relation between the existence of edge states and this topological bulk behavior or topological bulk invariance is what we call the bulk edge correspondence. Just one more thing. We call these states edge states. So edge states means that they have large amplitudes at the edges and almost 0 amplitudes in the bulk. And in the case of the SSH model, these edge states have 0 energy. They appear here in the gap between the two bands and always at 0 energy. As long as we have a condition, I'll talk about that in a second. Okay, very important also in the topological band theory is the symmetry classification of topological insulators. And usually this symmetry classification uses 3 symmetries: the time reversal symmetry, the charge conjugation on particle hole, or chiral symmetry or sublattice symmetry. The SSH model satisfies all of these 3 symmetries, so it falls into what we call the BDI symmetry class. But I'm not going to explain this in detail. I'm just going to show you the implications of the existence of these symmetries in the spectrum, in the band structure of the SSH model. So the SSH model has time reversal symmetry because the Hamiltonian is real. And that implies that its spectrum, this band structure that you see here, is going to be symmetric in a reflection about this vertical axis, okay? It's chiral, so it means it's symmetric in relation with the energy, the axis corresponding to 0 energy, okay? So it's the horizontal axis. And it has particle hole symmetry, so it means that the spectrum is symmetric in the inversion about the origin. This origin, it means this point over here, 0 momentum, 0 energy, okay? So this is important. I'm going to tell you why it is important. Because as I told you before, the edge states in the SSH model, they have 0 energy. And the reason they have zero energy is because we have chiral symmetry. And in fact, we can show that if you perturb the Hamiltonian, you introduce disorder, but this disorder is not does not break the chiral symmetry, the edge states will remain with zero energy. Okay, they will remain with zero energy. Okay, let's now. I almost forgot. Another important property of the SSH model is the fact that it has inversion symmetry. Okay, and in fact, in the case of the ring, any point in between two sides, consecutive sides, so we call mid bond point, will be inversion center. Okay, this point over here, this point over here, and so on. Okay, and one could show. I have to go fast because I have to to show the main results, and these are not main results. But one can show, in fact, that the polarization in this system is going to be quantized due to the existence of this inversion symmetry. Okay. Okay, let's now consider a slightly changed SSH model. Well, I call it slightly changed, you probably do not agree. So I told you that the SSH chain was a 1D chain with hopping terms T1, T2, T1, T2. So unit cell with two sides. Now, let's now consider a chain that is T1, T1, T2, T2. And then it repeats T1, T1, T2, T2, T1, T1, T2, T2. So the unit cell has four sides. Okay, unit cell has four sides. And curiously now, if it's a ring, this system also has inversion symmetry, but now the inversion axis is going to be this C site in the unit cell or this A site in the unit cell. So the inversion axis, it's never at the center of the unit cell. Okay, it's never at the center. That's important for what I'm going to show you in a second. So we have four sites in the unit cell, so we have four bands in the band structure. And curiously, we find, besides the four bands, we find edge states, but these edge states have finite energies. You see them here, okay? So it corresponds to this energy as T1 over T2 is changed. So they have finite energies, but they appear when T1 is less than T2, and they disappear when T1 is larger than T2. That's precisely the same behavior we have in the SSH model, okay? But if I calculate the Sachs phase for these bands, the Sachs phase is not quantized. It's not 0 pi, okay? It's not 0 pi. So we are going to, the calculation could give even higher numbers, but it would always be 0 pi, 2 pi, 3 pi, and usually it depends. On the others, we can do mod pi. Okay, mod 2 pi. Okay, what I'm saying here is that I have a problem here. First, I have finite energy edge states. So the usual chiral symmetry does not protect these states. And also, the Sachs phase is not quantized. And quite a few research groups, try to tackle this problem. How do we topologically characterize these systems? One of them was my group, okay? And we constructed a modified topological characterization that was based in modified parity operators, which are basically the aversion operators, and also modified Sachs phase expressions. And importantly, we also said that these finite energy edge states are protected, but not by the usual chiral symmetry, but by a hidden sublattice symmetry. Okay, that was one of the approaches. It's again, I'm going to talk about something different. There were other approaches. For instance, this one, where you split the Sachs phase in two contributions, one calculated between cells, unit cells, and the other calculated within the unit cell. This one is a very recent one, where you project the Sachs phase into a particular sublattice. And this one was also very interesting, where you have an artificial dimension. And then instead of calculating Sachs phase, you calculate the Shen number, for instance. But the one that we want to explain today, it's this one. We square the Hamiltonian. Okay, we square the Hamiltonian. So let me show you what this means. And I'm running a little bit behind. Sorry, guys, I'm running a little bit behind. Okay, let's assume a uniform chain. So a uniform chain, and I'm going to assume also it's a ring. So its tight binding model, it has this matrix representation you see here. It has nearest neighbor hopping equal to T1 and on-site energies equal to epsilon zero. Okay, it's this model that you see here, but now I'm going to set epsilon zero equal to zero. The reason is the following. Models or tight-bending models where we only have finite matrix elements in the Hamiltonian between sites in different sublattices, and here I'm just considering two sublattices, they are called bipartite, okay? So for instance, here, this model is bipartite because I only have finite matrix elements of the Hamiltonian between sites blue to red and red to blue, never blue to blue, okay? And when I have that kind of Hamiltonian, I have chiral symmetry. In fact, chiral symmetry, the chiral operator is just the projection in one sublattice minus the projection in another sublattice. But that's too much detail. Okay, it's models that are bipartite. I can define two sublattices and only have hopping terms between these two sublattices. They have chiral symmetry. Let's square this Hamiltonian. If I square this matrix over here without the epsilon zero, I get a block diagonal matrix. And you may not believe it, but it's there. It's there, and one of the blocks corresponds to the odd sublattice, odd side sublattice, and the other one corresponds to sublattice. Okay, the red and blue. And the one of these blocks, the block for the blue, corresponds to a tight-binding Hamiltonian with a hopping term T1 squared and local energies, local on-site energies equal to 2T1 squared. Okay, every site has this energy. And the other one, the other block, is exactly the same. In fact, these two chains, these two smaller rings, have exactly the same spectrum. Okay, and the eigenstates of the original ring can be written as the linear combination of the eigenstate for the blue sublattice plus the eigenstate for the red sublattice. But these two eigenstates must have the same energy. Okay, the red sublattice and the blue sublattice. And in fact, it's easy to show that why the spectrum is chiral. It's chiral because if we multiply the amplitudes in one of the sublattices by -1, we still get an eigenstate, but with symmetric energy. Okay. So what are we doing here? What we are doing is basically taking a chiral spectrum. This is the spectrum of this ring over here. Okay. We take this chiral spectrum and we square it. And by squaring, we fold the negative part onto the positive part, okay? So we would have all the levels on the positive part. But if we remove, notice now the following. If we remove this 2T1 squared, this blue ring becomes bipartite again. So again, if I remove these uniform local potentials, this ring becomes bipartite. So it will have again a chiral spectrum. So that's what we are saying here. We take a chiral spectrum, we square it, we remove some energy, and it becomes chiral again. And then I can do the following. Can do again the same. Square it, shift energy, obtain a chiral spectrum. For the uniform chain, I can do this until I reach two sites, for instance. And notice that I have here levels with different colors, and these correspond to the chiral level. And when I mean the chiral level is this central level here, okay, the zero energy level. So the different colors on the top, here on the top, correspond to the different chiral levels that are appearing. Notice also that it's a different chiral symmetry every time, okay? So I have initial chiral symmetry of the initial ring, I squared, I get this ring, I remove the uniform chain, uniform local potentials, I get a new chiral symmetry. These are different. So this can be generalized for any bipartite. Whoops. Sorry, someone is presented.
Sovik?
I think somebody is presenting.
No, stop that.
Preeti Mishra, can you please stop yours? Okay, now it's fine.
Oh, okay, I'll need to present.
Sorry for
again.
that, Ricardo. Yeah. Just speak on
sorry,
that.
Professor Diaz, you can continue.
You want me to? Do I need to stop presenting then?
No.
No, it is fine.
It's fine.
It's fine. Oh, it's fine.
Someone by mistakes just
Okay.
on that present, yeah.
Let me. Okay. I hope that you're seeing. Let me just put this larger because I don't know why, but it became very small here in my screen. Well, I know why, but I'll continue. It's not very fun. So I was just saying that we can do this for any bipartite model. Okay, any Hamiltonian that has this structure that you see here, okay, only off diagonal um, block, it only has one off diagonal block, so we can basically define a sublattice, and I only have hoppings between one sublattice to the other sublattice. This one, when squared, they generate this block diagonal matrix. Now, it's not mandatory that these two blocks have the same dimension. Okay, in the case of the uniform chain, they did, but maybe they don't have it. And if that happens, what the spectrum of two blocks is still the same, except that one of the blocks has extra zero energy states. Okay, extra zero energy states. So, and in fact, these zero energy states only have finite, only have support in one of the sublattices. Has this been applied to the topological insulators? Yes, it has. For instance, in this paper that you see here, people address the diamond chain with a pi flux. Okay, so when you have a diamond chain with a pi flux, all the bands in the band structure of the diamond chain become flat. You get a flat band with energy 2t, sorry, a flat band with zero energy, and another flat band with minus 2t. And if the diamond chain has open boundaries, it's not a ring, then you get also edge states. And these edge states have finite energy, as in the case I mentioned just a while ago. And they have, their energy is square root of t and minus square root of t. The Sachs phase of these free bands is not quantized, except the central band. Okay, but if you square this diamond chain, you get this spectrum over here. And now the bands that you have, they have quantized Sachs phase. Okay, they have quantized X phase. And notice that this blue band over here, it has two bands. It's generated. The two bands are the two bands. It's basically these two blue bands here, and only one red here. And one of these two blue ones is the chiral partner of the red one. Okay, it's the chiral partner of the red one. And in fact, we can remove again this 2t square energy, and we can say there is a chiral symmetry for these two, for this pair of two bands. And these edge states, in fact, are protected by this chiral symmetry. But okay, in the paper you can look some of these details. There have been quite a few already experimental realization of these square root topological insulators, okay? And this is the same paper that I've shown you before in a photonic lattice. But there are other realizations in acoustic lattice, topological lattice, even some mechanical with springs and masses, and they have done this, in fact. So acoustic lattices are interesting. It's basically a sequence of cavities connected by small channels where you create sound. It's basically that. And topoelectrical circuits are basically, it's electric circuits with capacitors and inductors and all of that. And you can simulate topological insulators and square root topological insulators on that. And here you have an example which is called the breathing Kagome. The breathing Kagome, it's a weak topological insulator and also a higher order topological insulator, but that's not something I want to discuss here. But anyway, you can see the edge states are here in blue and here in blue. So you see that they get finite energy edge states, okay? And these red ones are what we call corner states, but well, let's keep that. Okay, so I want to generalize this. I want to generalize this to high root topological insulators. How I'm going to do it? I'm going to introduce these sine cosine models. How long do I have? How much time do I have still?
Yeah, you have time. You have time at least 15, 20 minutes.
Oh, okay, that's good. That's good.
Ricardo, will it be possible to make it bigger? You are having difficulty in that because
this one.
Yeah. Actually, we are all seeing a small patch of your presentation.
Okay. Let me share it again.
Because of that glitch, I think something went wrong.
Oh, okay. Resume presenting.
Yeah. I think it's becoming. Yes. Yeah, I'm seeing it. It's becoming nice.
Screen, it was
yes.
large. It was large.
Yeah, it's fine. It is
That's
fine. Yeah.
Oh, okay.
It is fine.
Okay.
Yeah.
Okay.
Yeah.
So I was saying, I want to generalize these to high root topological insulators. How am I going to do this? I'm going to introduce a new type of 1D systems that I'm going to, well, call sine cosine models, so called sine cosine chains. The second simplest sine cosine chain is the SSH chain. The simplest one is the uniform chain. But let's consider the sine cosine chain. So the sine cosine chain, as I told you before, it's has a unit cell with two sides, and the hopping terms are T1, T2, T1, T2, and so on. If we divide these hopping terms by this square root, okay, by the square root of T1 squared plus T2 squared, then T1 over this square root becomes a sine, T2 over the square root becomes a cosine. So we get this chain over here, sine, cosine, sine, cosine, sine, cosine, and so on. If we square this, it's fairly easy to understand what appears here. Okay, let me explain just once. For instance, let's take a particle here in this pink side, okay? I'm considering the Hamiltonian squared. So the Hamiltonian does not generate just one hopping. Squared, it generates two. So a particle hops once, hops twice. Okay, that's what happens. So assume that we start at this pink site over here. It hops to the right with a hopping term cosine, and then hops again to the right with a hopping term sine. So the effective hopping term between this pink site and that pink site there, it's going to be cosine sine. And but we have other possibilities. We have this, for instance, the particle is here. It hops to the right with hopping term cosine and hops back to the initial site. That generates a cosine square. But we also have the possibility that this particle over here jumps to the left and jumps back. And that leads to a sine square. So we get cosine squared to come back plus sine squared to come back. And that gives one. Okay? So that's why squaring this chain over here, you get this chain over here. Okay? Fairly easy. Okay? Now let's introduce a more complicated example where the unit cell now it's larger. Okay? Can we do this? Look, it's a bipartite model. We can always square and get a block diagonal. But what I want is not to do this once. I want to do this several times. And that's what I'm going to call my generalization of the square root topology. Because square root topology, I could only do it once. But now I'm going to do it twice, 3 times, whatever. Okay? So I define here a sine cosine model with a unit cell that has 2 times n sides. And that means that we have n different angles theta. So I have sine of theta 1, cosine of theta 1, sine of theta 2, cosine of theta 2, until I reach sine of theta n, cosine of theta n, and then it repeats. Okay? So 2n sides in the unit cell, n angles. And if I square this, it's the same reasoning as before. So I get 1 everywhere. Why do I get 1 everywhere? In the pink sublattice. Because this pink sublattice is surrounded by sine of theta 1 and cosine of theta 1. So going right and back, going left and back keeps sine squared plus cosine squared of the same angle. But now the sublattice, the blue sublattice, it's not going to be the same as the pink sublattice, the Hamiltonian for it. Okay? Okay, that's important. In fact, the block corresponding to the blue sublattice is no longer bipartite. Only one of the blocks is bipartite, which is this pink sublattice after I remove this uniform chain, okay? Uniform local potentials. So I got this. And now what I pretend, what I want, what I want is to remove this energy and still get a sine cosine model, okay? Now it's not. You look here and apparently it's not. It's not a sine and here a cosine. It's something more complicated. But I'm going to select a particular set of angles that when squaring, I get again a sine cosine model. What I have here is exactly the same model as on the top, but just the bulk Hamiltonian. I'm going to say this very quickly. So when I have a one-dimensional system with a unit cell of a certain size, the bulk Hamiltonian is just the Hamiltonian for the unit cell, and then I close the unit cell on itself, and I put a flux, which is the momentum. That's the bulk Hamiltonian for 1D systems. And that's what you see here. So it's the same Hamiltonian for the unit cell, And then I close the unit cell on itself with a phase, which is basically the momentum. Okay, so I'm going to consider a particular set of angles. And then I will say how we define these angles. I consider a particular set of angles. And for this particular set of angles, I get this band structure that you see here. So this has 8 sites in the unit cell. So I get eight bands. And now I'm going to square it. Just the bulk Hamiltonian, because this is enough to give me the band structure as I square it. Remember that the bulk Hamiltonian is still bipartite, only has hoppings between pink and blue sublattice, okay? So it has chiral symmetry. And that's what I get. So I square it once, I will get a chain that's still bipartite, still has the sine cosine form, but has uniform local potentials equal to 1. I remove this, okay? I'll remove this 1. And in fact, it's not exactly of the sine cosine model, form, because it's multiplied by this global hopping, okay? This global hopping. Do you remember that in the SSH model, I had to divide T1, T2 over the square, divided by the square root of T1 squared plus T2 squared in order to get it in sine cosine form? It's the same. So when I square this model, I get this model over here with uniform local potentials equal to 1 that I remove. And this model is a sine cosine model times a global hopping factor, something that I multiply everywhere, okay? Now I take this one over here, I square it again, and this is only for one sublattice, as I mentioned before, okay? For instance, here, I only pick the pink sublattice, but here, I choose the blue sublattice. It can be whatever we want. And again, I get a model that has uniform local potentials equal to 1 that I remove. And again, it's of the form sine cosine if I divide this by some global factor. And in fact, this one is already the SSH model, okay? This one that you see here is the SSH model. And I can do this until I reach a unit cell that only has one site. It's the uniform chain, okay? So I start with this band structure. I multiply it, shift it, divide by some constant, I get this one. I square it, I get this one. Square it again, I get this one. And all of these have a new chiral symmetry, okay? All of these. Can we do the opposite? Because, okay, we started with the result, to be honest. Can we do the opposite? Can we start with the uniform chain and build this chain? And build this chain with the gaps that we want and the bandwidths that we want. Yes, we can, okay? In fact, the parameters that define the bandwidths and the band gaps are these global factors, these T0, T1, T2. If I know this, I know the initial band structure, okay? It's quite funny. I start with a uniform chain with only one band. I define these global hopping factors, and now I can do this step backwards. I can do it backwards because I have these expressions. These are the expressions that are going to define the angles of the top models. Okay, so I use these expressions, and these expressions almost uniquely define the angles. There is a small degree of freedom, but it's discrete, sometimes two solutions. Okay, so that's fine. Summarizing a little bit, the bandwidths and gaps of these corresponds to 2 levels here, 4 levels here, and oops, sorry, and 8 levels in the original lattice. Okay, let me go down here. Here I show you these are the top energies and bottom energies of the bands, and these are the folding. I call it the folding energies, but these are the levels corresponding to the sequence of chiral symmetries that are going to appear. And you see they only depend again on these global hopping factors. Okay, what about edge states? What about edge states? I have to go fast. What about edge states? So the reason we have edge states in the SSH model is because we have weak links at the boundaries. Okay, when I have a weak link means T1 smaller than T2. The last link is T1. T1 smaller than T2, I have an edge state. Okay, If it's on the left side, it's a left edge state. If it's on the right side, it's a right edge state. Here we have the same. If I have a weak link in the initial model, I'll have an edge state in the central band gap. But I square the model, I get another linear chain. If this chain has a weak link in the left, say in the left edge, it has a left edge where in this gap here and this gap here. So whenever I have here a left edge state, I also have it here, okay? And I can repeat this. For instance, the SSH model. If I get an SSH chain with a weak link, then I will have an edge state here, 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 okay? They get multiplied, okay. And all of these are protected by their respective chiral symmetry. But is that the real protection? Let me just show you this. If I introduce disorder that does not break the chiral symmetry, or two chiral symmetries, or three chiral symmetries, the edge states associated with these chiral symmetries are protected. I have here one example. Introduce some disorder, not in the values of, well, in fact, it's in the values of hopping terms, but I introduce disorder on the values of theta, okay? So this theta will have some Gaussian variation, and this one also like this, okay? If I do it like that, if I introduce this disorder, then I keep two chiral symmetries, the central one and these ones that are here, this one and this bottom one. And the edge states in these gaps are protected. Their energy remains always the same. You see that the dispersive bands get strongly affected by the disorder, but not the edge states. The edge states remain protected. There are other kinds of disorder I could introduce, but I'm going to skip it because I think almost at the end. I need still maybe 5 minutes. Anyway, I'm just going to show you very quickly the following.
Yeah,
So,
sure.
I have time or never?
Yeah. You can have 5 minutes at least.
Okay. So in this process, we created a direct root through tree of Hamiltonians. So basically, that's what we did. What you see, these vertical branches here are the blocks that I didn't describe, okay? But in fact, this is a network of Hamiltonians of smaller and smaller dimension with energy shifts at each step. And in fact, an eigenstate here in the original model, it's going to be a combination of eigenstates of all these blocks down there, okay? All these blocks. Okay, can we generalize this? Because was a very particular model. Well, I was thinking of talking about this one, but I probably am going to skip this one because I don't have time. It's not so simple, for instance, just a little bit. It's not so simple to generalize these sine cosine models to 2D. I can define them, of course, but they won't have the same behavior as the previous ones, that I can square it n times. In fact, I just can square it once, and I have to introduce magnetic flux. But okay, let me skip this and present you a general model. Okay, this is the general model or method of construction. So whatever the topological insulator that you have, you can construct a square root of it, and then the square root of the square root, and then square root of the square root of the square root. You can always do that. Okay, so what we need, for instance, look at here, we have the diamond chain. I want to build the square root of the diamond chain. So I want to find a model that squared one of the blocks is the diamond chain. I know that it must be bipartite, and one of the sublattices of this model must be the diamond chain. Oh, that's easy to do. Oh, it's very easy to do. I can create a model that's bipartite, and one of the sublattices is the diamond chain. It's here. Okay. I just introduce a gray site between two sides of the diamond chain. Okay, that's it. Okay, that's fine. Well, not so quickly, not so quick. Remember that it's not only to get the sublattice corresponds to the diamond chain. I must get local uniform potentials everywhere, and I must get the hopping constants of the diamond chain. Okay, in order I must get this model of here. So the hopping constants is not too difficult, because basically I know that the hopping term here times the hopping term there must give the hopping term of the diamond chain. So I just apply a square root to this is t, let's assume this is t, and apply a square root to that one. And this dimension with flux, and if I have flux, it's no problem. I just divide the flux by 2, because again, multiplying will give the right result. But what about the uniform local potentials? That's a little tricky, because if you look at these blue sites here, you'll see that this site over here, for instance, this site over here, has 4 neighbors. 4 neighbors. The coordination number is 4. But this one here only has 2. So the local potentials of this model, when I square it, when I get sublattice of dimension, won't be uniform. So I need to add another rule. And the other rule is the following. It's add extra sites, green sites. So I must create a lattice such that the blue sites, which are the sites of the sublattice correspond to the dimension, all have the same number of neighbors. So I added these green sites over here, and now this has 4 sites as neighbors, and this has 4 sites. So it's fine. Okay, that's a good way to do it. But there is another way. The other way would be to modify the hopping terms here. Okay, that's what I'm saying here. This would be another possibility. Instead of having extra sites, we just normalize the hopping terms. That's what I did in sine cosine chain. Okay, I normalized the hopping terms. And if you have open boundary conditions, you also need to do this at the end. Okay, you have either to normalize or to add extra sites. And here I show you. Whoops, I don't know why it didn't appear the text. Okay, sorry guys. I show you examples. For instance, this is the square root of the diamond chain. So we did again, okay? So this is 2 raised to the 4th root of the diamond chain. Did I say 2 raised to 2? I'm sorry. So it's the 4th or quartic root. Let's call it the quartic root of the diamond chain, okay? It starts becoming a little bit complex. Of course, you could choose only to normalize the sites, the hopping terms, and it will give this. But let's look, for instance, at the SSH model. The SSH model, we have seen this. Normalizing the hopping terms was the sine cosine chains. Okay, that's what we did. But we have this other possibility. And we would say, why do we have to, I don't know, understand why we have to add more neighbors, more extra sites, because all the blue sites have the same neighbors, two sites as neighbors. Well, they do, but the hopping terms are not the same, okay? The neighbors connected to the blue sites, they don't have the same hopping terms. And let me show you here, for instance. You see this blue one is connected to a gray, but this hopping term is different from that one over there, okay? And this blue one has 2 no dashed lines. So we must ensure that we have the same number of dashed and continuous lines. That's why the SSH model becomes the square root of the square root starts becoming very complicated. Okay, these were simple models, but we can do this for any model, in fact. Okay, we can do for the Haldane model. And you see it here. This is the spectrum of a ribbon of the Haldane model. This is the square root. And you see the 2 copies of the spectrum of the Haldane model. And this is the quartic group. It starts, it's very messy now, okay? And we can do this for many other models. Okay, I'm going to finish here, guys. I'm going to finish here. And so let me tell you what I presented here. Here I presented a generalization of the square root topology. So I presented the idea that it's possible to go beyond square root. Okay, beyond square root, you can go to quartic root or quartic root 2 raised to the 4th, whatever, 2 raised to the 3rd also, doesn't really matter. I presented this in 2 ways, okay? One was first addressing these 1D systems, which I called n times squareable sine cosines. The reason I chose this is because I could basically show a few properties in a simple way, okay? But then I presented a general method of construction of these I'm going to call it I-root topological insulators. And this is quite general, okay? I've shown the Shannon insulator, the Haldane case, but it's possible to do to semi-metals, graphene, and so on. We can higher order topological insulators. In fact, no, I'm not going to say that. So, and what do we plan to do? We plan to generalize this to any root. What I mean by this method I presented, it's just for 2 raised to some integer. root, okay? 2, 4, 8, and so on. And we want to do it for 3, 5, 7. Okay, we want to do it. We already know how to do it. We are basically finishing the paper. And we are working also with some groups on the experimental realization of these models in photonic lattices. In fact, we collaborate with the Barcelona group, and this Barcelona group collaborates with SMITE, with the group by Alexander SMITE, and that's one of the possibilities. And there is also something that we are doing, which is we can generalize this for any Hamiltonian, but it will give a very complicated result, and we call this factorization of Hamiltonian. So this is something which is incomplete. Thank you for your attention. That's all.
Yeah, thank you, Ricardo, for an excellent talk, a very inspiring talk. Actually, it generated a lot of ideas for us. I mean, at least for me, I should say, it was wonderful. I can see a couple of questions floating up in the chat box. I can maybe 3 questions. So I can read it for you, or you can, if you can see yourself in the chat box.
Let me see the chat.
Okay. So, okay.
Um,
There's a question from ICCMSP Presidency 2:48 p.m. The question is in 2D Chern number.
Into D, sorry?
It is a question about the 2D Chern number, which is equivalent to finding
yeah.
the flux of the Berry curvature. So,
Yeah.
can we somehow associate gauge invariance with Chern number?
Yeah. So the Chern number is gauge invariant.
Yeah.
Okay, so this is very well studied. Whenever you have the circulation of the vector potential,
Yeah.
the result of a circulation of vector potential is gauge invariant, not the vector potential, of course. Or
yeah.
if you have an open integral of the vector potential, line integral, that's also not gauge invariant. But when you close it, it is. Okay, so it's
okay, right. And the second question is again from one of our coordinators and students. Why are we not able to find the quantization of Zach phase in T1, T2, T2, T1 chain? I mean, is there any special reason that you don't get quantized Zach phase for certain variants?
Well, there is. In fact, it has. I have an explanation for that, of course. And the reason why it's non-quantized, if you calculate the Zach phase, in fact, we usually calculate it using something which is the Wilson loop.
Yeah.
And it's the Wilson loop. And the result of this Wilson loop depends on the parity values at the end of not the end, at
That is
special
how you
point.
close the chain, yeah.
Yeah. So, in fact, I can reduce the result of the Zach phase to the parity symmetries of the k equals 0 state and k equals pi state. And so, but in the case of the T1, T2, something interesting happens, and I'm going to show you. Let me see. It's this result over here. Let me just increase this. Which is, you have to do the inversion around an inversion center, okay? And the inversion center is here, okay? The inversion center is here. And if you do the inversion, you see that this A site leaves the unit cell. It leaves the unit cell. And that's the reason, okay? You get non-quantized Zach phase. You have to correct for that, for the fact that it leaves the unit cell.
Okay.
It will generate this exponential corrections here, basically. And so you have to take this into account.
Okay.
Of course, if you do the square model, everything's fine.
Yeah.
If you consider the square model, it's the SSH model again. So
yeah. I think the next question from Amrita Mukherjee is related to that. In squaring the Hamiltonian, is it you have squared the Hamiltonian, right? So is it the only way to go from non-quantized to quantized subphase?
Well, I would say it's the simplest one.
Simplest
Not
one.
the only one.
Not the
It's the
only one.
simplest
Okay.
one. For
And
instance, this one over here is quite smart. This is I'm not sure. This is not published yet. This is in archive. I think it came out maybe one or 2 months ago. And this uses a smart idea, which is the following. Let me try to explain. The edge state, the existence or non-existence of the edge state, in fact, is related with just one sublattice. Okay, because if you change, if you have the SSH chain with open boundary conditions, and you have an edge state at left edge, if you add an extra site to that end, you lose the edge state. Okay,
Okay.
so it depends how you ended your SSH chain. And so I thought this approach was quite interesting because he picked up that idea and said, let's just look at the Zach space in a particular sublattice. I liked it. And in fact, it's again related with the squaring because as we said before, squaring selects a sublattice.
Yeah.
Okay. But
Okay.
this, in this case, it didn't need to square it, but it's always there. Okay, it's always there. In the same way that here, when we defined this chiral symmetry here, this is the chiral symmetry of the squared model. This one over here. So it's, in fact, all of them have connection. The only one that does not have connection, I would say, it's this one over here, where they have the extra connection.
Right. Okay, I can just read out only one more question because we have a few more, but I will request the persons asking the questions to mail Professor Diaz because we have other talks now. And the last question I would pick up from this is from Moitra Kundu. Can you shed some light on how to the n root these may be experimentally realized? Can you really experimentally realize this?
Okay, I can. For instance, the first realization that we hope to do, we are working into frameworks, basically. We have one here, we are trying to do the acoustic lattices here in my department, but we are collaborating with people in Barcelona on photonic systems. And the sine cosine chains are very easy because we only need different hopping terms. And these hopping terms, so a photonic lattice is basically a silica crystal, and you carve waveguides with a laser. Okay, you can carve the waveguides with a laser. And the distance between waveguides defines the hopping terms. So the sine cosine chain is very easy to do. You just have to define these waveguides with particular distances. Okay, so that's easy to do. Also easy to do is topoelectrical circuits. Topoelectrical circuits now are very fashionable because you can do everything. You can do Hermitian models, non-Hermitian models. You can do great things with it. It's not very expensive, and we tried. To be honest, we applied to a project with people from Lisbon to do that, but the project was not successful, so that one is not going forward. But yeah, that's also another way to do it. And the acoustic lattices are also fairly easy to do. We are doing them with a 3D printer. We are printing the acoustic lattice and with a certain geometry, and then we are going to simulate these models there. But with real systems, that's more interesting. In fact, I'm going to tell you one possible way with real systems. Take a graphene sheet, okay, a graphene plane, and you start carving it, making holes. That's one way of doing it. You can change it in such a way that you get this high root topological insulators, in fact, a high root version of graphene. That's another way to do it. But that's experimentally a little bit more difficult. But that's another way.
Okay. Okay. I still see questions floating up, but I think we should, for the time being, stop here. And we must thank Professor Ricardo Diaz for a wonderful exposure to the topological issues of systems using very beautiful models, which one can definitely work out by hand and can look into many more possibilities. Ricardo, thank you very much. We
Thank you, Arnav. It was a
like to
pleasure.
have you with
Great
us.
to see you again.
Yeah. It was a real pleasure for me, and maybe I will be talking to you later about some queries of my own. But for the time being, I am handing over this session back to the coordinator with a big thanks to Professor Ricardo Diaz again for an
Thank
excellent
you
talk.
very much.
Thanks, Ricardo. Yeah,
Bye-bye.
yeah,
Bye-bye. I'm sorry, stopping the share.
yeah.
Yeah, so thank you, Professor Diaz, for this excellent talk. Also, I would like to thank AC sir for chairing the session. And here we are at the beginning of our oral presentation session at this afternoon part of the conference. And I would like to hand over the mic to Polomi to take charge of this session. So, Polomi, please.
Thank you, Shobik. Good afternoon, everyone. Now we are in our second session of oral presentation. Here we have two talks, and the rules remains the same for the speakers. You have 15 minutes for your presentation, and the next 5 minutes for our question answer session. I would like to request all of the participants to please turn off your camera, and also please keep yourself muted. You can write your questions in the chat box that will be addressed to the speaker at the end of the presentation. Now, I will like to welcome our first speaker, Dr. Narasimharao V. Avaru from Rajiv Gandhi University of Knowledge Technologies, Ongul. Are you there? Dr. Avaru, are you there? I can see him in the participant list. I guess he's.
He's yet to log in, I think, or maybe
I
I
think
can
he is
see.
there. He was there
I can
sometime
see
He is
him
back.
in the
he is
participants list.
he is still in the meeting. He is in the
yes.
meeting. He needs to unmute himself.
Maybe he is gone
It's a
somewhere
network
for
issue.
a yeah. Network issue. Maybe network issue. Maybe he has just taken a couple of minutes off due to some reason.
Yeah,
So
he
it's
has
actually
yeah.
Dr.
for
Avaru, you can unmute yourself.
Yeah, he writes yes, ma'am.
Dr. Avaru, you can unmute yourself and start your presentation. Can you hear us? Dr. Avaru, I guess he responded also in the chat box. Now it's over to you, Dr. Avaru. You can start your presentation. Is there any issues?
it is not clear what is happening. Just let me check.
He's writing his microphone is not on. Something.
Oh, he's writing something in chat box.
Yeah, a microphone no not. You can
Okay,
Oh,
there is a
my.
microphone button. You can just click on
Dr.
that.
Avaru,
That
you
will
can please try to turn on your microphone because your
You
presentation
can
is
turn on your
scheduled from
microphone and
3:45 p.m.
Yes, please click on your symbol of your microphone. That is the first step. I think he's rejoining. He's trying to rejoin. There must be some
yeah,
network
Okay,
issue. Yeah.
I think we can skip to the next presentation and just shuffle it back. Right, we have
yeah,
two
we
talks.
can do that.
Just let us wait for 1 minute, Polomi.
yes, sir.
In case he rejoins,
Okay, sir.
so
Okay, okay. Let us wait till 3:45.
otherwise we can ask the next speaker to start presenting. And just in that case, please write a message to Avaru that we are placing him next.